Okay, and I'm going to go quickly through using just SPSS the different situations that we might find ourselves in when we're looking at numerical variable and trying to determine whether the mean of one group, one experimental group and another control group, for instance, or two groups, two experimental groups, whether or not they're different or the same, the two means. So I'm going to open up SPSS. I'm going to try this with a number of different sets of data. I'm going to try it with a single sample compared to a known mean, two samples where the two samples have equal variances or standard deviations, two samples with unequal variances, and then also something that's called paired samples. So we're going to take a look at all the different possibilities that we might run into here. Okay, so I'm going to open up SPSS. So this will go a lot more quickly when we use SPSS than when we use, obviously, when we use Excel or some other calculator, when we try and calculate it manually. Okay, so I'm going to say open. Actually, this may be one of the ones I want, but close this. No, I don't want to close that. Okay, open data. And I'm going to go for single sample t-test. So in this situation, I've sampled 9 people. We got the same people that we had from the Excel test. And I want to compare the mean for these 9 people to a known mean for another population. In other words, this sample represents population B, but I want to compare that to a known mean for population A or vice versa. Okay, so I'm going to go up here to Analyze. And since I'm comparing means, I'm working with numerical variables, numbers. Since I want to compare means, I'm going to go down to under Analyze, Compare Means. In this case, I'm only taking a sample from one of the two populations. So instead of going to independent samples, so on and so forth, I'm going to stick with one sample t-test. I'm going to open that up. It's going to ask me what my test variable is, what I want to find the mean of. And I'm going to move that number, those numbers that I'm working with in here so the SPSS can calculate the means of those numbers. I'm going to let it know that I want to work with an alpha of 5%, same as confidence of level of 95%. Okay, and then I'm going to tell it what mean do I want to compare the sample mean to. So let's say that this population X looks like it has a mean of about 10. Let's say population Y, I know the entire population. In the case of X, I'm basing this on a sample, a small sample. In the case of Y, population Y, I happen to know that the true mean is 13 for population Y. So I'm going to put that in there. And it's going to compare the mean of this sample to the mean, true mean of the entire population that I'm comparing it to. I'm going to click OK, and SPSS is going to come up, and we'll take a look at what we got. Okay, so sample size is 9. Our mean came out to be 9.89. Our standard deviation was 2.934. Our standard error, which is our standard deviation divided by the square root of the sample size, 2.9 divided by 3, is 0.978. Now, SPSS calculated a t-score for us, and the t-score came out to be minus 3.18. Why did it come out to be minus? Well, it came out to be minus because it happened to use the 9 minus 13, the number that I was comparing it to, but it doesn't matter if it's a positive number or a negative number. I'm only interested in the magnitudes, the size of the t-value. So it comes out to negative 3.181. Okay, how did we get that number? We took the difference between the two means, the 9.89 and the 13. I believe it was 13 we were comparing it to, right? And it took the difference between those two and divided by the standard error, which was roughly 1. So it came out to be 3.18. So a t-score of 3.18 sounds like a pretty good t-score, right? But we don't know yet whether or not we can reject the null hypothesis that the two means are equal, Because we need to take a look at the critical value of t based on the sample size. In order to calculate sample size, in order to calculate what the critical value of t is, or look it up, we need to know the sample size or degrees of freedom. In this case, it's 8. Now, we've happened to done this before, so we know for 8 degrees of freedom and an alpha of 5%, that our critical value of t is 2.306. We looked it up before. Okay, so our t value that we calculated is 3.18, which is larger than 2.306. So I know I can reject my null hypothesis. SPSS takes this a bit further and actually calculates a probability of being wrong if I reject my null hypothesis. And what is that probability? It's 0.013. It's about 1%, a little bit more than 1% chance of being wrong if I reject my null hypothesis. Well, since this is less than my acceptable level of error, which is alpha is equal to 0.05, that also tells me I can reject my null hypothesis. Okay, so that's how I would deal with a one sample t-test, where I'm dealing with, I'll go up here again, where I'm telling SPSS that I want to compare the results of the mean of this sample that I took to a set value from another, in other words, a known mean for another population. That's one possible scenario that I might be in when I work with SPSS. The next one is open data, is when I have two samples. Okay, so I'm going to open this one up, and this is probably going to come up more frequently for you, because in this case I have 9 females and 9 males who I've taken measurements for, and I want to know if the two means of these two groups are different. You know what I'm going to do first? I'm going to do a little descriptive statistics here. I'm going to ask SPSS to tell me descriptive statistics, explore, okay, and I'm going to ask it to tell me put the values into the dependence list. That's, in other words, this first variable is values, the numbers, and put the gender into the factor list. Okay, in other words, divide up the means, all the descriptive statistics for these values by gender. Give me the information by for two genders. I'm going to click OK. Okay, and SPSS does that calculation for me, and indeed, the means for the females is 10. The means for the males is 7.56. Gives me a lot of other information about these two samples as well. But for the time being, that's what I'm interested in. The mean for females is higher than the mean for males. So now I want to actually see if with this data I can prove with 95% certainty, with less than 5% chance of being wrong, that the means of these two populations, not the samples, but the populations, are different. Okay, so we start with a null hypothesis that the mean for males is equal to the mean for females. We propose an alternative hypothesis. The mean for females is not equal to the mean for males. And we're going to decide whether to accept or reject that null hypothesis based on our desire for 95% certainty. In other words, not risking more than a 5% chance of being wrong if we reject the null hypothesis, that they're equal, and say that instead we accept the alternative that they are unequal. Okay, so in order to do this now, and here they are box plots side by side. They look pretty different, don't they? Okay, I'm going to go up to Analyze, except this time I'm going to go to Compare Means. And in this case, they're not a one sample t-test anymore. We have two samples. So it's an independent samples t-test. So I'm going to click on that, and I'm going to move the values into the test variable and the gender into the grouping variables. Again, you have to tell SPSS, before I do this, let me just show you in the background here. I'm going to go back to the data set. Wrong one. That's not the one I want either. That's going to be the last one I go for. Here it is, two sample test. Okay, just to show you, I'm going to go over here and I'm going to say View, and I'm going to turn off the value labels. And you can see that female is represented by the number 1 and male is represented by the number 2. Of course, we can go to the variable view and you can see gender under values. We've told SPSS 1 represents female, 2 represents male. Okay, so that's where that comes from. But I have to alert SPSS to this when I do the t-test. So I'm going to hit Analyze, Compare Means, Independent Samples t-test, 2 independent samples. I'm going to move the values, the numbers we want to find the mean of, into the test variables. And the groups, I want to break them up into gender, male and female, here. And I'm going to define the 2 groups as the number 1 and the number 2. And click Continue. And then I'm going to say, go ahead, let's go ahead and figure this out. So now what happens now? Well, let's take a look at this. What happens now is, if I look at this, now just as we expected, the mean is 10 for females or 7.56 for males. Standard deviation for the 2 groups. Well, look at this. The standard deviation for these 2 groups is pretty close to one another, right? And in fact, I'm going to go down here to the actual independent samples t-test and see how SPSS handled this. Well, it actually did the calculation twice. In the video that you saw before where I was doing this by hand, there were 2 sets of formulas. One for when you assume the variance of these 2 groups to be the same, as I might here, because one is less than twice the other, right? Or we would use a different row if we assume these standard deviations to be different, as I might if one was more than double the other. Okay, so if I go down here, I don't actually have to worry about having to make that judgment. SPSS makes it for me. And the way it does it is in these first 4 boxes, it calculates a Levine's test for equality of variances. And it comes up with this statistic which has a associated probability of being wrong, okay, if we reject the idea that the variances are equal. So if I look at this significance for these 4 boxes, has nothing to do with our t-test. It's only a test for equality of variances. If I look at this number, if it's less than 0.05, I say to myself, I'm willing to risk rejecting the idea that there are equal variance and using the second line, which is unequal variances. In this case, the probability is 24%, which is too high for me, too high a rate of error for me. It's not less than 5%. So that means I just fail to reject the idea that the variances are equal, and I stick with the top row. So if I stick with the top row, it means that the t-score I'm interested in is 2.184. And the degrees of freedom is 16. I can use that to look up my critical value at t if I want. And my significance is 0.044. Now, I'm going to cheat a little bit. And okay, let's take a look at this. 16 degrees of freedom. What's the critical value of t? So I'm going to go over here, 16 degrees of freedom. And the critical value of t is going to be 2.12 for 5%, an alpha of 5%. Okay, let's go back here. 2.12. Well, my t-score that I calculated exceeds 2.12. This is bigger than the critical value, so that means I can reject the null hypothesis that the 2 means are equal, means that the 2 populations are equal, and accept the alternative hypothesis. This is further demonstrated by coming over here, the significance two-tailed, and that's our p-value, our probability of being wrong if we reject the null hypothesis. And that turns out to be about 4%, which is less than the 5% that of my acceptable level of error, my alpha error, right? So that's more evidence. The t-score and the p-value, or the significance, are the 2 methods that I use to determine whether or not I can reject my null hypothesis. And in this case, I can reject my null hypothesis. Okay, so now, what's the next situation I might get myself into? Okay, I'm going to go Open, Data, and I'm going to open another data file here. And this data file, Okay, again, males and females, I turned off the value labels. That's why you see them as numbers, right? But it's another data set, another sample, another two sets of samples. They're independent samples, right? We sampled 9 females, we sampled 9 males, randomly selected, and so on and so forth. I'm going to analyze. I'm going to go to compare means, exactly the same thing as I did before. Independent samples t-test. I'm going to move the values into my test variable and gender into my grouping variable. And I'll remind SPSS that my two groups are the two values I have in there, 1 and 2. Click OK, and then I'm going to go ahead and make sure this option says 95%. Then I'm going to click OK. Can't say what I got this time. Well, this time, before I decide whether to use, well, let's go here first. Again, they got the same means for the two groups, but I have different standard deviations. I monkeyed with a number, so this would happen. And in fact, one is way more than double the other one. So it looks to me like maybe they're unequal. So I got to be a little bit cautious here. So when I go down to my SPSS page, okay, if I look at this, let's see, the top row is equal variances assumed. I'm not so sure. Looks like the standard deviations are different. So if I look across here, the first boxes I see are my test for my equality of variances. And my statistic for Levine's test is very big. And my significance, my probability of being wrong, if I reject the idea that the variances are equal and use the second row instead, my probability of being wrong is less than 1%, is only about 1%, which is less than 5%, which suggests I think I'm going to use that bottom row instead of the top row. Okay, as it happens, there's not much difference there, but there is a little tiny bit of difference. Okay, so my t-score is the same, 2.511, but my degrees of freedom is different. SPSS used that complicated formula that we saw in our directions before in order to calculate the degrees of freedom. And it's going to assume 10 degrees of freedom, which means that the critical value of t is going to be a bigger number. Smaller the sample size, bigger number critical value of t. So even though the t-score is the same top and bottom, the probability that I'm going to be wrong if I reject the null hypothesis is about a little bit more than 3% for the bottom row, but a little bit more than 2% for the top row. Both cases are less than 5%. So then, even if you would pick the wrong row, you would still reject the null hypothesis. But you can see that there's a little bit of a difference because of the sample size that's calculated from this, the degrees of freedom that's calculated because it's unequal variances, and we use that other technique. Okay, so, but in any case, we reject our null hypothesis. So, what are the three situations we see? Single sample compared to a known value, independent samples with equal variances, independent samples with unequal variances. Let's see what's next. Open, data. Okay, next thing I come across here is, what is this? Paired samples. I'm going to open this up. And in this one, I see that there are two, actually, the numerical variables. Let me change that to scalar, just so it's a little bit neater. You know, SPSS tends to think if you got integers and stuff like that, it may be nominal data. It may represent something other than the number. So at any rate, here's a drug test, except this one is a different kind of drug test. In this drug test, each person is represented by a row, and each person received the placebo, and each person received the drug. Let's make believe that this is a drug for reducing the pain of migraines. And let's say that these are effectiveness ratings or pain ratings or something like that from when people took the placebo versus when they took the drug. And maybe patient 1 took the placebo for 6 weeks, and then they took the drug for 6 weeks, and then they reported their pain level. And then patient 2 took the placebo for 6 weeks and the drug for 6 weeks. So these numbers, those side-by-side numbers, represent represent basically kind of before and after numbers for each individual patient, right? So they're not really, these are not independent samples. Each one of them represents the same subject in both cases, right? So what we're going to do with these instead is, instead of looking at it as a set of numbers that for the when we will for the placebo, and a set of numbers that describes the performance of the drug, we're going to look at the difference that it made for each individual patient. That's very powerful because now let's say that this group had 3 smokers and this one had no smokers. There's a variable that's introduced that we don't have control over. Let's say this group had 11 people that had high pressure jobs, and this one had people mostly who had blue collar jobs, not high pressure, right? Physical but not high pressure. So there's a lot of variability that we take out by using paired samples. We compare each person to themselves instead of different people. And the way we're going to do that is that by, instead of comparing the means for all the placebos versus all of the drugs, we're going to subtract one from the other so we find the difference for each individual patient. So for patient 1 made no difference. Patient 2 made 2 difference. Patient 3 it made 4 difference. Patient 4 it made -3. Patient 5 it made 2. Patient 6 it made 1, -1, and so on and so forth. So we're going to take a look at all of those differences. And then we're going to say to ourselves, did this drug make a difference, right? And in order to figure out if it made a difference, we're going to find the average for all of the differences. And the idea is that if there was no difference between taking the placebo and the drug, we would expect the average for the differences to be equal to 0. But if there is a difference, we would expect the average of the differences to be different than 0. So what's our null hypothesis here? Our null hypothesis here is that H null is that the differences equal, the average of the differences is equal to 0, or our alternative is the average of the differences is not equal to 0. Okay, I could write that this way. Mu for the differences is equal to 0, and mu for the differences does not equal 0. And if we get, if our value, if our, let's say that our average comes out to be 2.1, we want to prove that that's not equal to 0. So let's take a look at that. What's really happening here is we're going to take our mean difference and we're going to compare it to a set value of 0, right? Set value is 0. We've just done that before. That's what a single sample t-test is. So basically, paired samples is basically another kind of single sample t-test. So let me just check, see, I think I got a couple of questions here. So critical value is still 2.1. No, well, no, actually, critical value, I don't know how far back that goes. The critical value is based on the level of certainty. Okay, don't worry about it. Okay, it's based on the level of certainty, plus it's based on the degrees of freedom. So depending on which line you took, the degrees of freedom changed, right? Depending on if it was equal variances assumed or not. Okay, but yeah, you get the idea. Okay, so anyway, so let me calculate this now. I'm going to go up to Analyze. I'm going to compare means again, except this time I'm going to go to Paired Samples t-test. Okay, so now SPSS wants me to show it the pairs of variables. So the pairs are placebo and the matching person right next to them that's in the column called drugs. Okay, I'll just make sure this is 95% again. And I'll say OK. And then I'll go ahead and do our calculation. Notice it's down to 1 line again because there's only 1 sample, so there's only 1 standard deviation or variance. We don't have to worry about equal or unequal. So let's see what we get. We get a mean of 1.556. That means that the difference between the average for the average of the differences is 1.556. And we want to see if that's significantly different from 0. So the standard deviation is 2.98, standard error is 0.89, And eventually we're going to go over here and we're going to calculate a t-score. That t-score is 1.73, not too promising. And what's the degrees of freedom? Well, the sample size was 9 people, so the degrees of freedom is 8. So we know that the critical value of t for a sample size of 8, and sample size of 9, 8 degrees of freedom is 0.2306, 2.3 in other words. The t we calculated is only 1.7. So our t critical is less than our t critical. Our t does not exceed our t critical, so we fail to reject the null hypothesis. And just to demonstrate that that's really true, our p-value, our probability of being wrong if we reject the null hypothesis, is 12%, which is way more than our tolerance, our alpha, which was 5%. Okay? So we failed to reject the null hypothesis that the differences are equal to 0. We failed to reject that. Thus, we can't accept that they're not equal to 0. So even though it looked like there was a difference, the drug might be helping, we didn't have enough evidence to say with 95% certainty that that difference was not due to chance. Okay, so yes. I'm sorry. Well, we had single sample, we had paired samples with equal variances, we had paired samples with unequal variances. I'm sorry. I just misspoke. Let me start again. We have single sample, compare it to a known mean. We have paired sample with, we have independent samples with equal variances. We have two independent samples with unequal variances, and now we just saw paired samples. Okay. All right. Let's see. But it's paired samples is really like a single sample, right? Because we're looking at the different. We're looking only at the differences, which means that we only have a single set of numbers that we're averaging, and we're comparing that to 0. So it's basically just another kind of single sample t-test. Okay, so now analyze. Wait, let me open another data file here. Open, import data, open data. Okay, so now as in the video that you just watched, I went through an example where I opened the North Carolina birth data, and I did a t-test there. Okay, and I need to know. I need to work with a numerical variable. Could be the birth weight of the infant. Let's see, birth weight of the infant in ounces or grams, and I could look at it from the perspective of two values from a nominal variable. Let me pick something different this time. I'm going to see. Let's take a look if the birth weight of the infant is the same or different based on the gender of the baby. Okay? In other words, what would be my null hypothesis? The average weight for male babies is equal to the average weight for female babies. And my alternative hypothesis would be that the average weight for female babies is not equal to the average weight for male babies. Okay, so now these are all randomly selected people, women, births, right? So we have two independent groups, male babies and female babies, all randomly selected. So I'm going to go to Analyze. I'm going to go to Compare Means. They're going to be independent. There's not one sample t-test. I'm not taking male babies and comparing them to a known weight. I'm comparing the average male babies to the average of female babies in this sample, right? It's not paired samples because it's not the same baby before and after, right? It's independent samples t-test. I'm going to click on independent samples t-test, and I'm going to say, okay, the weight of the child in ounces, And the grouping variable is going to be the gender of the child. Okay, now I didn't bother to check to see whether that was, I'm going to cancel this and do this. Okay, let's see. The gender of the child, let's see okay, 1 is male, 2 is female. So those are the numbers I'm going to use. Analyze, compare means, independent samples t-test. Okay, so I'm going to move into test variable. I'm going to move the weight of the child. That's what I'm finding the average of. Test variable is always a numerical variable that I'm finding the average of, and that's the weight of the child. The grouping variable is always a categorical variable. In this case, it's the sex of the child. And I have to tell SPSS that the group 1, males, is defined by the number 1, and group 2, females, defined by the number 2. Maybe vice versa, I don't remember. Okay, options, I want to make sure it's 95%. Since I want an alpha of 5%, I'm going to click OK. Okay, good. So the average weight for male babies was 117 ounces. The average weight for female babies is 114 ounces. Now, are those two numbers far enough apart in order for me to reject the null hypothesis? Okay, so we're going to go down and we're going to do our t-test. We're going to take the mean 1 minus mean 2, 117 minus 114, which is roughly 3, and we're going to divide that by the standard error that we calculate. And we're also going to take a look at the standard deviation, and they look like they're the same. So the equal variances, equal standard deviations. So I think I'm going to be using the top row. And indeed, if I look at this test for equality, the significance is 0.326, right? Way bigger than 0.05, which confirms I'm sticking with the top row. I would only use the bottom row if this was less than 0.05. So I'm going to stick with the top row. So 117 minus 114 divided by the standard error, 3 divided by the standard error, right? Let's see. That's going to come out to a t-score of 1.928. And how many degrees of freedom? 798 degrees of freedom. That is the two groups, 800 altogether. There were 418 males, 382 female babies. That's 800 altogether, less 2, n plus 1 plus n2 minus 2, 798. So that's not even on my table, that number. Let's look at the table, just for the hell of it. Let's look at 798 on my table. Well, my table only goes up to 100. Look what happens once you get past 100. It gets so close to 1.96 that most statisticians might just use 1.96 because it's such a large sample size. SPSS is not just any statistician. SPSS is a machine, so it will actually calculate it, even if it's only the tiniest difference. Okay, so the t-score is 1.98 that we calculated. Our degrees of freedom is 798. The p-value, the probability I would be wrong if I reject my null hypothesis, is 0.054. In other words, my chance of being wrong if I reject my null hypothesis is about 5.5%. Okay, what's my alpha? Remember what my alpha was? 5%, right? So I have more than a 5% chance of being wrong if I reject my null hypothesis. So you guys online, do I reject my null hypothesis or do I fail to reject my null hypothesis? Fail to reject. Yes, you failed to reject because your significance came out to be more than 0.05, more than your tolerance for error, your p-value, probability of being wrong, in other words, if you reject. Okay, now technically you would reject your null hypothesis. In real life, I mean, it looks like we've really proved this. I mean, look how close this is. It's almost exactly 5%. This is so close to 1.96, a t-score of 1.96, which would be what we might use with this big a sample size if we were doing it manually, rather than, our table wouldn't tell us what it might be 1.97 or something like that. So it's really close. It's really a close call here, but closer than I thought it was going to be. I think this is the first time I did this particular combination. Okay, would it have made any difference if I had gone with the second row? Well, my t-score would have been a little bit bigger, but my degrees of freedom would have been a little tiny bit smaller, and in fact, my p-value is exactly the same. Okay, so it would not have made a difference in this case. So there you go. We failed to reject the technically failed to reject the null hypothesis, even though it really looks like we came really close. In other words, you would probably still publish this, but you would just indicate that the difference between your means suggested a p-value of 0.054, right? Instead of just saying you reject the null hypothesis. Okay, so I mean that's what happens in that case. Okay, so now there is one other ugly thing that could raise its head. Okay, and I think it might be in that sheet that I gave you. Hang on a second, let me see if I can get back there. Get all this other stuff out of the way. Do what I have? Portions. I don't have an example of it there. Paired samples. Let me see if it's in that. Have extra steps. T-test variations. Yeah, here we go. Now, what about if you have a proportion? Right? Why not use this for proportions as well? Okay, so now how are we going to do that? Well, when we're dealing with proportions, our p-values, our proportions, for instance, say we take a sample of people from whose diet includes a lot of olive oil, and we're comparing them to people whose diet does not contain a lot of olive oil, and we want to know whether one group has a higher rate of diabetes, higher prevalence of diabetes than the other group does. Okay, so we take a sample of 100 people whose diet has a lot of olive oil in it. Say eat a Mediterranean diet. Let's phrase it that way. And we found that the proportion of people that have diabetes in that population is, let's say it's an elderly population, is 15%. And then we take a similar random sample of 100 people that are Americans and eat an American diet that are between 60 and 80 years old. And we find that the proportion of people in that population that have diabetes is 20%. In other words, 20 out of 100. First one is 15 out of 100. Second one is 20 out of 100. And we want to know whether I can say that those two proportions, those two prevalences of diabetes in those two populations are different. In other words, what's my null hypothesis now? My null hypothesis now is that P for the prevalence of diabetes, P for diabetes in Mediterranean diet is equal to P for diabetes in American diet, people following the American diet. What's our alternative hypothesis? That P Mediterranean does not equal to P American, right? So same idea, except the point value now is not the mean, but rather the proportion. Okay, so now I have the same problem as before. Now I want to compare the two of those. I want to do a t-test that's based on them. Well, first of all, when you do this kind of analysis, you almost always deal with large samples, right? When you're doing a sample based on proportions. Okay, so for the most part, we don't bother using the t-test. We use the z-score. Okay, and one of the rules we're going to follow is that we want a large sample, right? But we want to make sure that in any sample that we take, there's no fewer than 15 people in either the have it or don't have it part of this thing. Remember I said 15 out of 100? In other words, we don't want 14 out of 100. That's too small. We should take a sample of 200 and maybe get 28 out of 200. We don't want to do it if it's only 100 out of 14 out of 100. So we want at least both sides of that, people who have diabetes and people who don't have diabetes, to be greater than 15 for each one of the two samples, right? So in this case, it happens to turn out, right? 15 out of 100, 20 out of 100. So in both cases, it's more than 15. So now, since I have two proportions, right? Well, you guys may remember that when I was looking at confidence intervals, You guys remember what we used for the standard error for confidence intervals when I was looking at proportion? Okay, if I was looking at a proportion like P cap is equal to 60%, right? And I wanted to know what the confidence interval for this was. Well, again, we were dealing with large samples, so I knew that my confidence interval, 95% confidence interval for P, right, the true proportion, is going to be P cap plus or minus, and since it's a large sample, I use 1.96 for my 95% confidence interval, not a t-score, times my standard error, right? So how did I calculate my standard error? Well, my standard error was equal to the square root of P times 1 minus P over N, right? And that's how I calculated my standard error. 0.6 times 0.4 divided by the sample size, let's say 200, and then I would work that out, find the square root, and then I would fill that in here, and I have my confidence interval. Maybe it came out to be 0.52 to 0.68 or something like that, right? Whatever it came out to. That's how I calculated my standard error. Well, you know, I got a problem now. Now, when I'm in this example that I just gave you, 15 P cap for group 1 is equal to 0.15. P cap for group 2 is equal to 0.2. So now, which of those do I use for my standard error? I got the same problem I wound up with before. Well, how do I deal with this in terms of calculating my standard error? Okay, well, we have a formula here on this table I gave you. Let me go back to the table. And the way we're going to do that, we're going to calculate a pooled P cap for both samples. And how are we going to calculate that? The pooled P cap is going to be equal to P cap 1, 15%, times N1, which is the sample size 100, plus P cap 2, 20%, times the sample size of 100, divided by the total sample size of both of them, which is 200. And that's going to give me a pooled proportion. It's kind of a weighted average again, right? And what am I going to do with that? Well, then I'm going to use that pooled proportion down here, right? This P is the pooled proportion. Okay, so I'm going to use that pooled proportion for P times 1 minus P times 1 over N1 plus 1 over N2, the sample sizes. That's going to be my standard error. And the difference between the two proportions is going to be the top of this equation. So this is going to be 5%, right? 20% minus 15%, 5%, divided by what my pooled proportion is. I got time to calculate. Why not? Let's calculate it and see how far we can get with this. Let's do this torturous calculation, just for the hell of it. Okay, yeah, good. PCAP pool. Oh, good. I think you guys are following it online too. So let's actually calculate this. Let me get this over here. Good. So now, okay. So I am going to do my pooled proportion is going to be P pooled is going to be equal to 0.15 times times 100 plus 0.20 times 100 over 200. So it's going to be an average, right? It's going to be 15 plus 20 over 200. 0.20, okay, is equal to 35 over 200 is going to be equal to 0.175. No big surprise. P pooled. P cap pooled is going to be equal to that. So now I'm going to use that to calculate my z-score. My z-score is going to be equal to, the difference in the two, which is 0.20 minus 0.15, over the square root of, and I'm going to calculate this out here, so it's going to be a little easier for me. I should have used Excel, right? Okay, so I'm going to calculate this out here. So that square root, it's going to be the square root of 0.175 times 1 minus that, which is 0.825, right, times 1 over 100 plus 1 over 100, square root of that whole thing. So that's going to be the square root of 0.175 times 0.825 times 1 over 100 is 2 over 100, or 0.02. Okay, I think I got that right. Okay, so I'm going to calculate that whole thing. So clear this too. Okay, so 0.175, anybody dispute me there? Times 0.825 times 0.02 is equal to this whole thing, and then I'm going to find the square root of that, and that's equal to 0.05. I'm going to round it off to 0.05. Okay, just to keep our calculation a little bit simpler. Okay, so this whole thing is equal to 0.05. Okay, so if I go back here, this whole thing on the bottom is equal to 0.05. Our z-score is 20 minus 0.20 minus 0.15. 0.05 divided by my standard error, which is 0.05, which is equal to 1. What is my critical value of z in order for me to have less than 5% chance of being wrong? In other words, 95% certainty. Okay, what my value is z? What would my z-score have to be? What do we use for a 95% confidence interval? What value is z? 1.96 is my critical value of z. Did I exceed my critical value of z? Nope. So I fail to reject my null hypothesis, right? In other words, I can't say that P1 is different. I can't reject that P1 is equal to, actually, we're dealing with, when we put our null hypothesis, or whether it's a proportion or an average, we're always talking about the population in our null hypothesis, right? In other words, the proportion for population 1 is equal to the proportion for population 2. I fail to reject that. I don't say that that's true, I just fail to reject it. So I can't say that there's a difference between the Mediterranean diet and the American diet, because maybe my sample size wasn't big enough, maybe the difference wasn't big enough. In other words, there was too much of a chance that this outcome would have been something we would get by chance, rather than there being a real difference between these two populations. Okay, so we have proportions that we can deal with. So what's the key here? It's always a numerical variable in one form or another, right, that we're working with, and it's in two groups. All t-test, always two groups. Never three groups, never four groups, always two groups. Well, that's kind of a limitation, isn't it? It's a limitation because, among other things, well, let me see. Let's say I wanted to compare four ethnic groups in terms of their average total cholesterol. Okay, let's say Caucasians, let's African Americans, Asian Pacific Islanders, Hispanics. Okay, let's start, say, four groups. Okay, and let's say that the mean, I take a sample sizes, different sample sizes. There's 100 people here, 110 people here, 120 over here, then 50 over here. Asian Pacific Islanders are hard to find here, around here. Maybe I'll make that one 80 or something like that. Okay, let's say that I find the mean for each group. For Caucasians, the average cholesterol randomly selected population of Caucasians in the population, the average cholesterol was 130. For African Americans, maybe 140. For Asian Pacific Islanders, 160. For Hispanics, 125, let's say. So now I want to prove that there's a difference, that there's, based on ethnicity, there's a difference in the average cholesterol level for these four groups. Okay, so I'm really interested not in X bar, what I calculated from my sample. I'm really interested in mu for each group. So what's my null hypothesis? My null hypothesis is that mu for Caucasians is equal to mu for the average cholesterol for African Americans is equal to mu for Asian Pacific Islanders is equal to mu for Hispanics. That's my null hypothesis. My alternative hypothesis is that at least two means are different. Not that they're all different, but at least two of these groups are different from one another. Okay, could I do this with a t-test? Do you guys think I could do this with a t-test? Could, right? How would you do with a t-test? T-test only works with two groups. So you would do it two groups at a time. For instance, I would say, okay, first I'm going to do it with, I'm going to say Caucasians versus African Americans. Then Caucasians versus, do a t-test. Then Caucasian versus Asian Pacific Islanders. Then Caucasians versus Hispanics. Well, then, wait a second, there's another group. African Americans versus Asian Pacific Islanders, and African Americans versus Hispanics. Wait a second, we didn't take into consideration Asian Pacific Islanders and Hispanics. We didn't compare those two means. So we would have to do, let's see, 3 times 2 times plus 1. We'd have to do 6 t-tests. We'd have to do a t-test 6 times in order to test all the different possibilities. Okay, what's the probability of being wrong if I do my t-test? When I do my t-test, what's alpha typically? 0.05, right? Well, in addition to being a lot of work, I have to do it 6 times. Each time I do it, I have a 5% chance of being wrong, right? So now, if I got a 5% chance of doing wrong at the first time, then I got another 5% chance of doing it wrong the second time, another 5%, another 5%. It's kind of like Russian roulette, right? Sooner or later, the odds are going to pile up and I'm going to be wrong, right? So we need a mechanism to do all of these at once, right? So I want to have a way that I can prove that this is not true, reject that idea, and say that this is true. But I don't want to inject extra error by doing repetitive t-tests. And I don't want to do a ton of work here doing t-tests over and over and over again. And what if there had been 10 ethnicities? Then I would have to do like 60 tests or something, or 100 tests or something like that. T-tests. It wouldn't work very well, would it? So we have another tool. We have a new tool. And the way that new tool works is it looks not just at the mean, but it looks at the variability between these different groups. So think of it this way. Okay, let's say that the mean of I'm going to look at 3 groups. Group A, mean for A, mean is equal to mean for B, is equal to mean for C. Okay, the distribution of samples that I might get for group A might look something like this, right? I'm going to make a number line here. Say this number line is 100, 110, 120, 130, 140, right? Let's say group B, the average, the average I get for that and the variability based on its average and variability, repeated samples might look something like this. And for group C, it might look something like this. Well, group C is so different from these others that it's so far away that it's easy to tell that it's different from these other 2 groups. And just by looking at the distribution of the sample means, I can tell it's different, right? Well, maybe I can take advantage of that. And the way I can take advantage of that is I can look at the variability, the variability within the groups and the variability between the means. Okay, well, what does that mean? That means that I can have a situation where, this is one mean, this is another mean, this is a third mean, where the means are so far apart, it's easy to tell the three groups are different, right? Okay, so if the means are far apart, that's a good thing. It's easy to tell it's easy to prove that the three groups are different. However, well, gee, the means could be far apart, but if the variability is really big, well, there's so much overlap. How can you be sure if you took a sample from this one, it wouldn't be this sample from this group instead of this sample from that other group, right? When you took the mean. So you're concerned about the variability within the groups as well as how far apart the variability between the means is. So what's a good thing here? A good thing is when you're dealing with small variability within the groups and a big difference between the means, big distance, big difference between the means. So we can invent a statistic called an analysis of variance. We're going to call it F. And that statistic is going to be based on two things. It's going to be based on some measure of the variability between the means, and some measure of variability within the groups. Okay? And the bigger this F score is, the more likely it is that we can reject our null hypothesis and prove that they're different. Okay, and how do we get this? Well, how does this equation work? Well, the way this equation works is that the bigger the difference, in other words, this is the numerator, this is the denominator, right? Okay, the bigger the top of this is, the bigger that my F score is. The smaller that the variability within the groups, the bigger my F score is, right? So we want this number to be big and this number to be small. The smaller this number is, the bigger the F score, the bigger this number, the bigger the F score. So we can actually create a new distribution where we can say, based on how many groups we have, the number of groups that we have, right, number of groups, the number of samples within the groups, we can create a new distribution called the F distribution, or analysis of variance, where we can predict how likely it is that at least two of these means are different from each other based on how big this F score is. And these sample sizes, right, and these numbers, the distance between the means and within the groups, that'll give us an F score. And that F score we can compare to a critical value to see if we can reject the null hypothesis that mu1 equals mu2, mu3 is equal to mu4, etc. Right? So we're going to take advantage of calculating the variability between the means, how far apart they are, and how variable the values within each group are. And we're going to take advantage of that to see if we can't reject that null hypothesis and accept an alternative hypothesis, which might include that this mean is equal to this mean, or another mean is equal to another mean, without having to do repeated t-tests. Okay. Now, how do we do that? Well, there's the rub. It's not that easy. Okay. And if we go to Blackboard, and remember, we're going to go over this on Monday too. Okay. If we go to Blackboard, I posted sessions. Oh my God, it's making me do this again. I'm definitely going to wind up forgetting how to spell my name. Can't move it up, making this thing make me log in all over again. At least it remembers it. Okay, so I'm going to go in here. Okay, and you'll see that we have, there's a lecture for analysis of variance. We're a little early, but for that lecture, because I was, if you look at the syllabus, I think it's actually scheduled for Monday. Actually, chi-square is scheduled for Monday, and then the test was immediately afterward. But I wanted to introduce this earlier, so we didn't have just Monday to look at it and then wind up getting tested on it very quickly. So if you read, you can go through the lecture here. Now it may be that my demonstrate. If you go down here in the bottom part, these are three demonstrations. One is kind of a hokey way that I put together of explaining this. Okay, this first one, it's 4 parts. This first one is a hokey way of explaining this. This second video is an actual calculation of this quantity called analysis of variance by using Excel. I'm not going to expect you to do that because when you will go through it, and you'll see how I wound up doing this. Okay, so, and the third thing here is how to do what I did with Excel over here. Instead, do it with SPSS much quicker and much simpler, and use SPSS to demonstrate, to do this function analysis of variance and reject our null hypothesis. Only problem with that is that if you reject your null hypothesis, that mu1 does not, that mu1 equals mu2 equals mu3 equals mu4 equals mu5 you can once you say that that's not true, I can reject that and accept my null hypothesis. The next question becomes, well, are all of them unequal, or only 2 of them unequal, or 3 of them unequal? Right? Now, which ones were unequal? SPSS has a function where you can use called post hoc tests. Post hoc means after the fact, and you can run those tests to determine which of your means are, if you've succeeded in rejecting your null hypothesis, then you run the post hoc test in SPSS, and that will allow you to identify which of the means are different from one another, statistically significant, right? Not just that some of them are different. Okay, so these videos I think will step you through it, and we're going to go over this on Monday, but I think if you get a chance to go through these before Monday over the weekend, it'll help you like really understand this stuff. So when we come back on Monday, we can actually apply this to some examples and prep for, and really be better prepared for the exam. So if you guys could, like go through this and play these videos. You can play the lecture also, or maybe we'll deal with the lecture on Monday. But I think it would be a good idea for you to actually take a look at this exercise and see how this stuff works. For,
which sessions are we reviewing?
For the tests, we're going to be doing everything since the last exam, which would be, let me go back to sessions, which would be, since the last exam, 5, session 6, yeah, which would be maybe some confidence intervals, t-tests, and analysis of variance. Yeah, session 5 through, session 5 through 9. I'm not going to go back to central limit theorem, but because we're applying central limit theorem really, so I wouldn't be too worried about that. But yeah, confidence intervals, calculating confidence intervals, doing t-tests, and mostly with SPSS. The confidence intervals may be manually, because it's not that complicated. Okay, t-tests, maybe single sample I might ask you to do manually, but anything more complicated than that, probably SPSS. And analysis of variance, almost exclusively SPSS. Session 5 was t-test. T-distribution, we talked about t-distribution. Then session 8, we went into the actual t-test and so on. Session 5 was central limit theorem. No, I don't think so, because you're applying central limit theorem, you're already applying. And it's going to be similar to, I'm going to be posting some more homework stuff too for you to practice on as well. I'm going to give you at least a homework on the t-test and homework on the analysis of variance, so you have something to practice with between now and then. Okay, and we'll have maybe I'll have a weekend session where we go over the homeworks, and the homeworks will kind of be similar to what the tests are going to be. And the second test, well, but you have to have it done by the test night, let's say, right? Makes sense, right? You're gonna want to do it by then anyway, so you know how to do it. So I'll get them posted the next night or two, the two additional homeworks, and they'll be a good guide for you for what's on the test. Okay, and again, you get more than one shot at the homeworks. So, yeah, we're moving pretty quick, but I mean, 8-week course. You guys wanted to get it done in 8 weeks, and you want to do 16 weeks in the regular semester, so it's your fault that we have to go so fast. I appreciate this. I appreciate for a lot of you that's first look at this stuff, and it is very challenging to cover so much material in such a short period of time. But I think we'll do it. And the test will be similar. There might be some short answer, multiple choice, kind of like judgment kind of stuff. And then there'll probably be some basic problems and applications for SPSS. Might be a little thing where I throw in like a table from SPSS and ask you to interpret some stuff. But I'll try and make the homeworks similar to at least what the problem portions of the exam are going to look like. So good night, guys. We'll catch up with each other on Monday night again. And like I said, I'll post a couple of homeworks, and I'll set up something for an hour on the weekend where we can go over those homework problems or similar problems, so that you're a little bit better prepared for what might show up on the test on next Wednesday. Okay. And then after that, we're talking about chi-square and correlation and regression. And we're closing in on the end of the semester pretty quick, right? Yeah. So, okay. Take care. Good night, guys.